Well, where do we get those mass percent composition numbers? One way is if we know the chemical formula, we can calculate it from the formula. So there are different ways to do it, but I think the easiest way is to find the mass of 1 mole of the compound and the mass of your element that you're interested in that is in 1 mole of the compound. And then it's times 100 to get percentage. So the mass percent of element X is the mass of element X in 1 mole of the compound divided by the mass of 1 mole of the compound times 100. The only reason that we're doing 1 mole is because it makes it simpler. Okay, you could choose some other amount, but choosing 1 mole makes it easy. Because whatever element X is, we can just look at the periodic table and see what the mass of 1 mole is. So that's why we choose 1 mole, just to make it easier. Let's look at acetic acid. So acetic acid is the acid of acetate. So you take acetate ion and you stick a hydrogen ion on, you get acetic acid. That's the active ingredient in vinegar. That's what gives vinegar its distinctive vinegar smell. We're asked to calculate the mass percent composition of oxygen in acetic acid. So the percent oxygen is going to equal the grams of oxygen divided by the grams of HC2H3O2, the mass of the part divided by the mass of the whole times 100%. And we're just choosing to take a 1 mole sample. So how many moles of oxygen are in a mole of acetic acid? 2. It's O2 here, right? Let's calculate, I'm kind of going around about, sorry. Let's calculate the molar mass of this, because we're going to need it, and I'm going to show you something that's kind of nice about this. So here's our formula, HC2H3O2. You could group those hydrogens together for the calculation, or you could leave them separate. It doesn't really matter. I'm just going to leave them separate. There's the 1 hydrogen and 2 carbons, and another 3 hydrogens, and 2 oxygens, so I've got 1.008 plus 2 times 12.01 plus 3 times 1.008 plus 2 times 16. 60.052 grams is equal to 1 mole of acetic acid. So that's the mass we want in the denominator. That's the mass of the whole compound. 1 mole of the compound, 60.052. I'm letting that 2 come along because I want to avoid rounding errors. Okay, since we have that written out, this part right here, that's the mass of oxygen that's in 1 mole of that compound. And this will happen with any formula. If you write out calculating the molar mass like this, identify which of these terms corresponds to the element that you're interested in, and that's all you need. You could go ahead and multiply that out, or you can just copy it down. That'll be 2 times 16 grams. And that's going to be times 100%. The grams are going to cancel out. So I've got 2 times 16 divided by 60.052 times 100. and I'm getting 53.28715 blah, blah, blah percent. Did you get that number? How many significant figures should that have? 4. The molar masses that I used all had 4 significant figures. And so I end up with 4 sig figs here and 4 there, and so this is going to have 4. And so we're going to say, well, that's 53.29% oxygen. That 39% for the sodium in sodium chloride, if we calculated it this way, we could get 4 significant figures easily. If you use a periodic table that has more digits on its molar masses, then you could have more significant figures. Any questions? This number then could be used as a conversion factor in future problems.